Hello and welcome back to the lectures on high-performance scientific computing. We will now continue our discussions on OpenMP. These slides credit again belong to Argonne training program on exascale computing from 2024, which was conducted at the Argonne National Labs. So in the last lecture, we had just introduced the concept of OpenMP and we had talked a little bit about the Hello World program. We had written a simple program which would just print out Hello World, and we had made it multi-threaded. We had seen how we could get the thread ID numbers and ask each thread to identify itself using that ID number. We will now go ahead a little bit with this discussion on OpenMP. Just as a reminder, OpenMP execution model uses what is called as the fork join parallelism. You have an initial thread which begins like a serial program and it spawns a team of threads as needed. The number of threads that need to be spawned can be controlled, and you can keep increasing the parallelism until whatever performance goal you need is met. You can also do nested parallelism as we had mentioned in the previous class. Now, when you create OpenMP threads with the parallel construct, for example, in this program, you have the array A which contains 1,000 elements. You are now then setting the number of OpenMP threads to 4, and then you have the parallel section. Now each thread has a certain ID which is now assigned to individually to this variable ID. And a function called poo is called, which is basically passing the ID and the array A. So for each thread from 0 to 3, because there are 4 threads, each of the ID numbers would go 0, 1, 2 and 3. That would be passed along with this array A. So what essentially that is happening is that each of the code will run the same, or rather each of the thread will run the same code redundantly. The only difference that will happen is that the ID which goes in as a function parameter. So the program flow will be such: you come in over here, you have a declaration of the array A, then you set the number of threads to be 4, and then you call this function. You call this function 4 times because you're doing 4 number of threads. Each of this function is passed the entire copy of A, which is shared between all threads, and you pass the individual ID, and until each of these functions are complete, the program will wait, and then because this printf is outside the parallel section, that means all the parallel threads here will be destroyed and only one single printf of all done will come out. So there is sort of an implicit barrier here at the end of this parallel section. That means until all the threads complete this function poo, the program will not go ahead to this printf. So there's an implicit barrier over here. We also need to be aware that the copy of A is now accessible to all these functions and all these threads. Now, we set the number of threads using this function called OMP setNumThreads. But sometimes on certain operating systems, you might not get the actual number that you request. You might get fewer than that. These are due to constraints in the operating system. Because remember, if you look at the stack that we had discussed in the previous class, finally the operating system is the master scheduler. It will hand out the resources which are there, and certain operating systems will not allow you to set number of threads beyond a certain threshold. So you might actually get fewer number of threads than that you request. But once a team of threads have been launched, it will not be reduced. In a sense, dynamically, you will not see a reduction in the number of threads. If n threads are launched, that means n threads will exist. And each of those threads will execute the exact copy of the code which is there within the structured block. The only thing that will change are the operands, because each of these structured block of codes will have different operands because, for example, ID over here will be different for each of the threads. Obviously, there could be common variables like n threads, which is the total number of threads which is there in the team, that could be put over here. And you would need this for certain algorithms, and we will see that in a reasonable example pretty soon. So essentially what this code does is that you have a runtime function which requests a certain number of threads, which is set over here. This entire code block is sort of then executed. This is another runtime function which returns the actual number of threads which are there in the team. And this function is now being run from 0 to n threads minus 1. Now let's look at some mathematical problem. Finally, this is a course on scientific computing. We have to solve real world problems. So let's look at the problem of numerical integration. And let's say that we need to estimate the value of pi. Mathematically, we know that if we integrate within the limits of 0 and 1, the function 4 over 1 plus x squared dx, we would get to the value of pi. Now, we can do this by hand analytically, but let us try to do this numerically. So if you want to compute this integral, what we essentially do is we break up this function into n small rectangles, each of these small strips, where the height of each rectangle is the functional value at the ordinate between the limits of this 0 and whatever the x coordinate is of the upper bound. So somewhere on the midpoint of this triangle. And what we do essentially is we take the sum of all these small rectangles, which is the summation of I from 0 to n being the number of rectangles that we choose, f of xi multiplied by delta xi, where delta xi is the small width over here. And since delta xi is always uniform, we can pull it out. We can say the summation of f of xi from 0 to n will multiplied by delta x will approximately equal to pi. So what we really need to do is evaluate f of x at several of these intervals in the middle of the interval I, right? So if I were to look at a serial program, I will now say how many steps I want to take. Now it is quite obvious, the more number of steps that I take, the more accurately the answer that I will get, but the harder effort that I need to put in. So just for an example's sake, we will take about 100,000 steps over here. The serial program will look something like this. So I have the variables x, pi and sum to be declared to be 0. Now I have the step size, which is 1 divided by the total number of steps that I would like to take. That is 1 divided by 100,000. Now I will loop over all the number of steps that I need to take, okay, which is going from 1 to number of steps. And for each of those steps, I will then figure out what is my x value, and then I will figure out what the functional value is, and I'll add it to this sum. And then finally, pi is the step size multiplied by the local sum of these functional values. So this is how I would compute serially. Now each iteration will be done one at a time, but this is akin to almost an embarrassingly parallel problem, because evaluating the areas of these rectangles can be done parallelly at the same time. The one thing that I can't do parallelly is computing the global sum, which will give me the result of pi. So let's see what I can do first to figure out some timing. Because finally, remember, what we would like to do is figure out how much faster I can go if I used a parallel machine. So I will include OMP.h to get some library functions in. I will get a timing function. The library routine get OMP w time basically gives us what is the wall clock time, or how much time it's taking to execute this program. So I will see what the initial time is, Then I will put another clock over here and figure out what the final time is, and then it will tell me how much time I took to compute pi in how many seconds. So that's still a serial program. Now, how do I create the parallel version of this program? So I need to figure out what are the shared variables. I need to figure out what the private variables are. I need to keep a close eye on that. And in addition to where I put in the parallel construct, I will need to put in runtime library routines, figure out how many number of threads are active, what is the particular ID of each thread, which is done using OMP get thread num. I need to look at timing, and obviously I can also set the number of threads explicitly in the program. So now let us see how we can construct the parallel Pi program. So we use the parallel construct OMP parallel. What is the challenge that we have? We need to divide these loop iterations between threads. Each of those rectangle calculations now must be spread amongst multiple threads. And then we have to have a local accumulator for each of the threads, which will hold the partial sum of the areas for each of the threads. And then we need to compute a global sum. So we need, apart from the parallel construct, we need to figure out how many threads are at work. We need to set the number of threads, and we need to figure out each of the thread ID. Having the timing also will be useful. So this is the parallel Pi program, which is single program with multiple data. So let's walk through this. So we still use the same number of same number of steps. We now have 2 threads. This can be modified to whatever number we want, but we say that we would like to have 2 threads. We have defined a variable called numthreads2, and we have done this in the program definition so that we just need to change this to do it in the whole code. We do not need to go inside and meddle with the code. We say we have now a local sum array, which is sum the total number of threads, because we need to each thread will have to calculate its local sum so that you do not have any sort of a race condition. We have the step size, which is being calculated over here. We set the total number of threads using the OMP set numthreads function. Then we have the parallel section which comes in. First thing that we do is we figure out what the identification number is for that particular thread using the OMP get thread num, and we assign it to the variable ID. Now we must remember that whatever variables are declared within the parallel section, these variables are private variables, in the sense that each thread will have its own particular copy of it. Okay? So you have numthreads ID, which is being created over here. Now numthreads tells me what the total number of threads are, and that is put into this variable. Coming to this statement, we say that only one thread should be making the global sum. So I say I assign this to thread ID 0. There's no particular reason why I need to do it to thread 0, but it just makes it convenient. So if I say my ID is equal to 0, I then say n threads is equal to number of threads. So the thread 0 now has the information how many total number of threads are there. Now in the next for loop, what is essentially happening is that you are going from your ID, which is either 0 or 1 in this case, because there are only 2 threads, till you go to the number of steps, and you are skipping the total number of threads. So that means if I have 2 threads, each of the threads are skipping every alternate other rectangular block, and it is then computing what is the x, and then it is putting it as a local sum. And then finally over here I am computing what is the local pi by looking at each of these, some of these steps, total number of threads. This part is, you can see, is being done serially. The last for loop is not in the parallel section. It is actually outside the parallel section, right? So this part is the global sum is now being computed serially. So you can change the number of threads to say 4, then every fourth thread will be, or rather every fourth rectangle will be skipped, and each thread will keep doing every fourth rectangle. So this is something called something sort of a cyclic distribution of the rectangles which need to be used to compute the numerical integration or the area under the curve. You could have an alternative solution to this as well. You can make it region wise. You can say that you have, say, 2 threads again, but now I will set that the first half or the first set of rectangles will be computed by thread 0, the second half will be computed by thread 1. If there are more threads, you can take this entire region between 0 and 1 and chop it up into bigger blocks and assign each thread of these blocks. That is the program flow for this sort of thing. This is called blocked distribution. So you could do cyclic distribution or you could do block distribution. From a computational perspective, it doesn't make too much of a difference at this point of time. The answer that you get should be the same. Now, let's see a little bit of the timing results. Now, remember the timing results that you obtain on each machine will be slightly different because of the specifications of the machine and what is being run, the type of compiler that is being used, so on and so forth. So the timings that are being reported over here are for these specifications. So if I use one thread, I take about 1.86 seconds. If I use 2 threads, I get 1.03 seconds, the answer in 1.03 seconds. 3 threads, it actually increases to 1.08 seconds, 4 threads to 0.97 seconds. Now, remember whenever you do this sort of timing study, it's always advisable to run the program multiple times because there are certain other overheads always associated with the operating system, and it's better to take sort of an average number. Usually the ideal case is that you take about an average of 5 runs. So you can see that the performance, as I keep increasing the number of threads, is not actually linearly increasing. It's not really giving me a quarter of the time when I go to 4 threads, even for this fairly embarrassingly parallel problem. Now, most of these programs, single program, multiple data program, basically runs the same program on different processing elements, which are P. And essentially what you're doing is that you're chopping it up between different P ranks. Now, the numerical integration that we did was between the limits of 0 and 1. It could have been between any limits that you wanted. We could do similar mathematical tricks with any sort of geometrical problem as well, where we chop it up into several parts and then we do the compute and then we do sort of a global reduction. That's essentially the fundamental idea in any parallelism. This is the same kind of algorithm or logic that we will use when we deal with MPI programs, where we run these codes on distributed memory machine. And this is the bedrock of parallel programming. Now we will talk a little bit about performance related to these issues. Because remember, when we looked at the timing of the calculation of pi, we were not getting the best performance that we wanted. So let's look back and look at the performance of parallel programs. Now, there are n independent tasks on one processor. Now, if I look at the sequential time that it takes, if let's say I'm doing it serially, the total time it takes is to load the program, do those n tasks, and the total time which it consumes for getting the results. Now, if I have n independent tasks which I can now distribute amongst P processors, the total time that will take in parallel is the time it takes to load up, the time it takes to compute these parallel tasks which can be run concurrently, and then finally what is the time it takes for the reduction or to consume the results. So we talk about speed up as the increased performance when I use more processors. So essentially speed up, which is a function of the number of processors that I use, is the ratio of the time it takes sequentially divided by the ratio of time it takes parallelly. So if I have perfect linear speed up, that means that I have no parallel overheads. So if I give a program 10 processors, the speed up will be 10 times. That means the parallel code will take 10 times less than the sequential code. If you have speed up greater than P, that means it is superlinear speed up, and this is typically due to cache effects. We had talked about the different hierarchies of memory, because typically as the number of processors grow, you typically tend to store the data more locally in cache, and the problem starts to fit in cache, and you might end up getting superlinear speed up. But these are certain rarities. But most of the time you get speed up which is less than P. So we will now come back to Amdahl's law. What is the maximum speed up that can you expect from a parallel program? And we had discussed this earlier. So we had said the speed up depends on the serial fraction of the program alpha. The maximum speed up when you use P processors is 1 over alpha plus 1 minus alpha by P, where alpha is the serial fraction of the program. If we have unlimited processors, that means P tends to infinity, the maximum possible speed up now is 1 over alpha, and that is essentially Amdahl's law. You can see that if our program is 90% parallelizable, our maximum speed up that we can obtain is only about 10. If our parallelizable fraction is 0.999, the maximum speed up that I can obtain is only about 1000. So how does Amdahl's law affect our problems? So how does Amdahl's law affect our timing problem over here? You can clearly see that there is some initial time that is required to calculate all the preliminaries for the program. It takes some amount of time to create the threads. The destruction of threads at the end of the parallel segment also requires some amount of time. This is a sequential operation. And then finally, computing the global sum requires a parallel time. So when you add up all these things, it's quite clear that the serial portion increases. The serial overheads also increase with the increase in number of threads, because there is some time which is now devoted to management of threads. So if I increase the number of threads beyond a certain reasonable threshold, then I will see even slowdown of the code beyond what it takes for a serial code. For example, for a simple program like this, if I had initiated maybe 1000 threads, I might get a time which is worse off than 1.86 seconds. So what we really need to figure out is how to control these internal variables and how to control the number of threads in a team. We really need to figure out, tune this number to the number of optimum number of threads, and we can always reset the number of threads using this OMP set num thread. Now, is there an easier way to do without recompiling the program? Yes, we can do this using the environment variable which we showed you earlier. You set it at the bash prompt and we say export OMP num threads, and we can set it to the exact number of threads that we want. The key over here always is to pick the optimum number of threads for a particular size of the program, and that depends extremely on the hardware. So the most important thing is first to do a timing study of whatever program you write to see what is the optimum number of threads, and it depends on the problem size as well. So here is an exercise which I leave you with. Go back to your parallel program for Pi, see how it scales with the number of threads, try to explain it using Amdahl's law, try to figure out what might be going on. See this as a homework assignment. Thank you.